So our third class, and we actually may get through 2 classes a day, I don't know, because like I said, from here on, I always spend the most amount of time on the first 2 classes because they're the greatest detail. Plus, once you kind of get a feel for it, you can kind of see where, they're not that much different. It's easier. Plus, I always spend the least amount of time typically on the gated ion channels, just because of the fact that we have covered that kind of stuff in very detail previously, and the other classes cover that, and the nuclear receptors, because there's just not as, they follow their own kind of rules. So if we just had to imagine, and you're told that these were called receptor guanylyl cyclases, what do you suppose they're going to do, just based off of their name? Has to do with cyclic groups, and what kind of cyclic groups? Guanylyl ones. So just like, where have we seen that kind of name before? It wasn't guanylyl cyclase, but it was adenylyl cyclase, and adenylyl cyclase made what compound? Camp. So hypothesize, what do you suppose guanylyl cyclase is going to make? See, the GMP. So that's why it's the guanylyl. It's made off of made off of the guanosine instead of the adenosine. So this is just to show you. So ultimately, we can see where we're going here, where you start with a GTP, and you're going to make a cyclic GMP. Fortunately, it doesn't have a nice little camp kind of moniker that we can say, but it's going to make cyclic GMP. That's why I said this is really fairly simple. There are 2 broad classes. Now, remember, in particular with this chapter, we do a lot of comparing and contrasting. Okay? So with both of the first 2 that we're talking about, the RTKs and GPCRs, remember there's an external signal, it binds externally, and then there causes some kind of conformational change on the inside. Well, with guanylyl cyclases, there's a couple of differences. One thing, and there's some similarities. So if we just look at this, we can see that there are 2 types of guanylyl cyclases. One is what we have been used to seeing so far, where we have the external binding portion internally. It's going to cause a change. There is another, and this is one thing that's different than the others. There is actually one type of guanylyl cyclases that are soluble, and so they are intracellular. Okay, it doesn't have an extracellular component. So not all GCs are like that, but there are some. And these, by the way, are activated by nitric oxide. All right. So yes, I uploaded the one that just has the boxes and not the answers. But yeah, so there are 2 types. Right? There's a type that what we've seen in the past, which has the transmembrane domain. So we have an external binding event, causes an internal signal. And then we also have the type that's only internal, and that one is actually activated by nitric oxide. Okay, that's what the NO stands for. Okay. So knowing what we know from the previous examples, remember CAMP was made by adenylyl cyclase, and then that adenylyl cyclase, after it made CAMP went on, and what enzyme did it activate? PKA, protein kinase A. So just hypothesize, what do you suppose that CGMP is going to activate? Right, so that's it. I told you, it's really, really quick and simple. So then PKG goes on and it activates a whole host of things. Right? And then since we already know about the cyclic nucleotide phosphodiesterase, which helps break down CAMP, one hint is when they have that generic kind of name, that means they're usually more promiscuous, and so they take that whole broad class. And so since it's a cyclic nucleotide, phosphodiesterase can also help break down CGMP as needed.
So all we really need to know from that one is that there's 2 different classes.
2 different classes. It's similar and I can't, because if I go back, it's going to want to completely do it. But if I just draw that portion that was on that pathway, actually here, I don't have to do that. I'm just going to go to the 4th group is the gated ion channels, but go to here. But I'm going to go back and talk about this one. What you can see is we have this external event. So whatever it is that the example of whatever its stimulus is, and whenever it does, it turns on. The enzyme is actually a part of that. So one way it's different than the GPCRs, which used CAMP, is that the enzyme, the guanylyl cyclase, is a part of that transmembrane complex. Remember, the GPCRs, it caused a conformational change that caused an activated G protein. G protein then it jumped over to adenylyl cyclase. Adenylyl cyclase was not a part of the original binding apparatus, for lack of a better word. Now, the one exception to that is the one that's activated by nitric oxide. Nitric oxide is only intracellular. There's nitric oxide is involved in lots and lots of different things. It's a second messenger in of itself, and it's involved in everything from from erectile function to production for lactation. It's involved in uterine contractions. It's involved in vasodilation and constriction. So there's lots of different things that nitric oxide is involved in. Okay, so then this next section, so to speak, like I said, we don't spend a lot of time on each of the last four, because I wanted to focus primarily on the first two, are the gated ion channels. And so what do you suppose gated ion channels do? Like, what's an example that we've seen in the past? Like, you have calcium ion channels, we have the sodium-potassium ones, and there are lots of examples of that. I'll pause it. Okay, so the points I want to make sure is what this does, or what gated ion channels do with respect to signaling cascade, is it's going to convert an external signal into an electrical signal. And we'll look at an example in more detail in a moment. Let me change this. Right? Secondly, the electrical signal, that's a change in membrane potential. So we can talk about, hyperpolarization, where it becomes more ionic on one side versus the other side, that kind of thing. Is a change in membrane potential. So what are some examples where we see these kind of hyperpolarizations? What are some of the systems that utilize these? Right, muscle contractions. That's a big one. So these are examples. What's another example? Just think about parts of your body that have to require electrical impulses. Pardon?
The heart.
Right, so that would be with the muscle contraction. Mm-hmm. The nervous system. Your senses, a lot of your sensory systems do that, which we'll go into examples of that. And then, like learning, memory. Hopefully some of yours are firing off synapses right now. And some of the examples, we actually already talked about this. Sodium is a big one, potassium, calcium. Make sure calcium is a 2+. Does anyone know what's one of the, perhaps the only negative monoatomic anion that's used? Well, if it's negative, it has to be an anion. Which anion? It's a mono, meaning we don't have to worry about like glutamate, which is anionic. But what one? Instead of we have sodium cation, potassium cation, calcium cation. What's the anion that's used? Chlorine. Mm-hmm. Well, technically chloride, right? But yes. Yep. Those are the biggies, the big four. That's not to say they're the only ones. Like I said, we have other ones that cause, electrical changes. But those are the big four. Okay, so this was just an example of one. This is the Sodium-Potassium Atpase. I said it was from last chapter, but I don't know if you guys are able to go over it or not. But just in general, it's a gated ion channel. And so the way that it causes hyperpolarization is that sodium and potassium are both used, and they both have a +1 charge. However, if you look at this, there are binding spots for 3 sodiums, but there's only binding spots for 2 potassiums. It's also called an antiport because they're going in opposite directions. So as 3 sodiums go out, 2 potassiums come in. So that's why it causes an overall more positive charge on the inside than on the outside than on the inside, since 3 went out and 2 came in. And so this is just an example. Otherwise, without that, they typically would go through, if it wasn't some type of, they would just go along the gradient, right? If you have too many sodiums on the outside, it would flow into the inside and vice versa. Now, it can be much more complex, and so this is something that you probably should be reviewed from like anatomy, physiology. And so this is for neural transmission, and it shows you the fact that it can be much more complicated, and it can be an amalgam, a mixture of different processes. Okay. So we have what's called the presynaptic neuron and the postsynaptic, and of course this is the synapse or synaptic cleft. Okay, so that's where between from one neuron to the next neuron. And so typically what happens is for the action potential to occur is it starts in the presynaptic and then follows down to the postsynaptic. So the first, what happens is the sodium, I think it hit square. The sodium ions will flood in whenever they become open, and then that's going to cause the potassium ions to flow out. It's called efflux. Okay, but there's a split second or fraction of a second difference between the two. This flows down the axon until we get to the calcium. So what happens here is whenever they get excited, they're going to open up, so calcium now will flood in, and calcium then signals, if you get too much calcium in here, for the vesicles that contain acetylcholine to be released. Then the acetylcholine is called a ligand-gated ion channel, because it's a ligand that's going to come in, and it's going to bind to its own receptor on the postsynaptic neuron. In order for it to go from one neuron, the signal will go from one neuron to the next neuron. Okay. It's this opening or this activation that triggers the opening of the sodium ion channels and the next, and what had been the postsynaptic neuron, to continue the signal down. Sodium then will all trigger the potassium flows out, calcium then will flow in, calcium builds up down there at the next synaptic cleft, will open up the acetylcholine, and the signal is propagated that way. So, I don't know why it makes it so big. So the neurons can have additional receptors. There are different neurotransmitters. This is acetylcholine. I don't ask that you memorize this. I would give you the structure for it. And I guess, I wouldn't figure that you'd be able to do formal charge and everything like that. But it's acetylcholine. This portion of it, or is the acetyl group. This is what choline looks like. Okay, choline is a tetramethyl. It's a permanently positively charged because it's a tetramethylated or alkylated, I should say, nitrogen. Okay. All right, so then I wanted to bring this up because, as again, the neurotransmitter can have different, and hopefully by the end of this lesson we actually go into more details. Right, so this is the first one that I wanted to talk about. So does anyone know or recognize what this one is, the one on the left? It's not tryptophan directly. Because why is it not tryptophan? It does look like tryptophan, doesn't it? Looks an awful lot like tryptophan. In fact, that's one that where. And so it's right. We have this OH group that's not there, And tryptophan. But what else is missing? If this was tryptophan, this neurotransmitter is derived from tryptophan. That's where the question is, what does it resemble?
Is it missing the backbone?
Right, it's missing part of the backbone, right? Because it's got an amino group, but what does every amino acid have? Carboxylic acid is missing. So we'd have the amino, that's the C alpha. But that C alpha, and this is the R group except for the alcohol. This is the R group. See, it doesn't have the carboxylic acid hanging off of it. It's been, what you'll find out is a lot of the neurotransmitters, or many of them that are derived from amino acids, they get decarboxylated. So they're amines now. In fact, you may have even heard about monoamine oxidase inhibitors, MAOIs. Those are inhibitors of that process. Okay. And so that's why once you start to kind of get a feel for this and those enzyme names and seeing the same kind of things over and over again, hopefully, I don't want you to have to sit there and memorize the entire book, but if you understand the logic behind it. But no, this is derived from tryptophan. It is, see, does it always revert back? No. This one, by the way, is serotonin. Okay. And it's also called 5-hydroxytryptamine, which kind of makes sense. It looks like tryptophan, but it's an amine, and then it's got that hydroxyl group on it. And so that's why sometimes I even abbreviate it as 5-HT, 5-hydroxytryptamine. So if I write that out, since I forgot to put it on this one, 5-hydroxy tryptamine. All right, then we have this neurotransmitter right here. Does anyone recognize this neurotransmitter?
It looks like glutamate.
Yeah, is it glutamate?
It's not. Actually, it is.
It is. It's glutamate. And glutamate actually is also a neurotransmitter. And so, yep, that's just glutamate. So I just wanted to let you know in there. And so there are neurons that have receptors for glutamate. So here's another example. Okay. What about this neurotransmitter? Does anyone recognize it or know what that would be called? What? Well, it's got an amine. What else does it have on it? Carboxylic acid. And so if it's got an amine and a carboxylic acid, it would be it's an amino acid. It's glycine. That's glycine. Because see, the C alpha just has 2 hydrogens. I know you're just not used to seeing it that way. That's why I always throw this one in there. But glycine is also a neurotransmitter. Okay, and it's using their receptors for glycine as well. Okay, and so then here's this one. If we look here at A, what is this one? That's glutamate once again. This is drawn a little differently. Okay, but technically on the paper that I got this off of, there's a typo. They call it glutamic acid, but it's already lost its carboxylic acid. It's glutamate. All right, this is glutamate. This one right here, what's the only difference between the two? It's been decarboxylated. It's missing its carboxylic acid, this one right here. And so this one, you may have heard it. I mean, it's called gamma amino butyric acid. Yes. Except, there's a space between butyric and acid. Okay. It's also called gamma aminobutanoic acid, if you think back to, or here it'd be gamma aminobutyrate, or technically it'd be butyrate, or gamma aminobutanoate. So think back to organic chemistry. Remember, it's got 4 carbons. So we look here. No, that'd be ground 0, because the carboxylic acid gets to 1, 2, 3, 4, and so that's why butanoic acid, the old term for butanoic was butyric, and so that's why I put it. But it's also, does anyone know what the nickname for gamma aminobutanoic acid is?
Is that BY?
Yeah, it should be BU, I'm sorry. That's supposed to be BU. Good catch. BU, not Y. The second one's a Y. All right, for 4. What does anyone know what is more commonly called? It's called by an acronym. GABA. Okay, so this is GABA. That's where GABA comes from. Now, knowing what we know about the enzymes and the enzyme names, what class or classes of enzymes do you suppose does this? Turns glutamate into GABA. What class of enzyme is it? This is decarboxylase. That's the last word, the last name, if you want to think of it that way. Decarboxylase. Many times usually they're named after their substrates, once in a while they're named after their products. So if you were going to name this one, what would you name it? What specific decarboxylase would it be? You could say GABA, or what's its substrate? Glutamate, and this one's glutamate or glutamic acid decarboxylase. Here, I'm going to go ahead and just abbreviate because I don't have enough room. And it's also given an abbreviation called GAD sometimes.
So, if we were to write GABA decarboxylase, we'd get the same, like, would that be correct? Or?
Well, I mean, usually in the very beginning, I'd give you most, if not all, the credit.
Okay.
But by the end, you're going to get a feeling. But yeah, since this one's literally, that's why if you know their names, you can figure out what they do. Or if you figure out what they're doing, a lot of times you can get a good feel for what the name of that enzyme would be. This one's GABA, right down here. It's just drawn differently, that neurotransmitter. I don't know why. Okay. And I just wanted to point out that then we have, let me go ahead and it's on the next one. It's been last, because I would try to bring it home a little bit. So I did on that one. So it's the same figure, but just to let you know a little bit about, there are two types of GABA receptors, called GABA A and GABA B. And there are lots of different drugs that are either agonists or antagonists to these GABA receptors. And they're used as treatments for many, many different diseases. That's why this paper is trying to show originally. And so the GABA A are chloride channels. Okay, and so what it does is it allows for hyperpolarization. And what it is it decreases the excitability. And the reason why is if you think about it, if there's so many chloride ions that are out, it can't get re-excited as easily. Does that make sense? So, because it's going to take longer for the chloride ion concentration to come back down in there. And so it decreases the excitability of the cell. Whereas GABA B is one of those transmembrane, remember we talked about those that transpass 7 times, it's a huge complex. It uses a GPCR. And what it does is it actually inhibits a calcium channel, okay? And it activates potassium channels. And then, as I mentioned, there are lots of different agonists and antagonists. You can see where, if you think back to if any of you had taken medicinal chemistry or anything, you can see like what's called the now if I wouldn't have thought of it, the pharmacophore. I'm like, no, it's got a 4 in there. It's completely simple. What the pharmacophore is, where it's very similar to GABA, so we can kind of see that kind of backbone-looking thing over and over again. Some of these are a little bit more difficult to tell than others. This one uses a sulfur instead of a carboxylic acid. It's called the pharmacophore. But some of these are agonists and some antagonists. I always point out personally Baclofen. This is one that I take. Baclofen. Does anyone use what Baclofen was used to treat? It's used to treat people who have neuromuscular disorders where your muscles contract too much. And so like dystonia, sometimes multiple sclerosis, okay? Certain things, certain diseases like that. So what it does is, since it's an agonist, does an agonist act like GABA, like the GABA receptor, or is it going to not act like GABA? Does it turn on or turn off? Right, it turns on. It binds and it behaves the same thing as GABA would. So it keeps it where my GABA Bs would be on more frequently than they would be. Whereas if it was an antagonist binds and it doesn't have that same effect. It wouldn't turn on that cascade pathway. So for me, when the baclofen comes, it binds on, it turns on that GPCR. that GPCR helps control muscle contractions. Okay, so it helps keep the muscles from having so many spasms and from being turned on all the time. This is just one example, once again. Whereas if, you wouldn't want to take necessarily the antagonist, because then you would have the exact opposite effect if you did that. Okay. Right. So are there any questions?